At first glance, this single bright source, this smudge, this grouping, doesn't look like much. Images like these are translated for our eyes, and it's because our eyes only can perceive a small region of all the frequencies of light. Astrophysics is much more than just capturing different wavelengths of light. Many objects or phenomena are simply too far away to directly image. A lot of data comes from pixel-sized point sources, and those points provide astrophysicists with a powerful window into what makes up the universe. Even now, most of what scientists learn about the cosmos comes from studying light. Astronomers can work out distances, speeds, sizes, temperatures, and the composition of elements because matter behaves in predictable and consistent ways. They do this by literally prying these photons apart. This is spectroscopy explained. Spectroscopy is the study of how matter interacts with light. And it all began with a prism, like this one. Light entering one side of the prism bends or refracts as it passes through the triangle shape and exits out the other side. All of the wavelengths enter together, but they exit as a rainbow-like spread of colors. What's happening is that the shorter, more energetic wavelengths, like blue and violet, bend a little more than the longer, lower energy light, like red and orange. Because they bend at slightly different angles, the wavelengths separate, fanning out into a band of colors. NASA has a whole fleet of telescopes that can split and study a wide range of light on the electromagnetic spectrum, not just the light that our eyes can detect. So Hubble can detect through the visible spectrum, but also a bit into the infrared and the ultraviolet. Webb is just infrared and can look at the light that is emitted from billions of years ago. And of course, the images from Webb are really spectacular, but this is what flutters the hearts of scientists. This spectrum shows a light that penetrated the atmosphere of a planet called WASP 96b. The light being measured comes from the planet's host star, some of which skims through the atmosphere. Humans are a long way from directly imaging exoplanets, so telescopes like Webb will use spectroscopy to find those chemicals that could support life in their atmospheres. Which is why Webb's first spectra is so amazing.
You're actually seeing bumps and wiggles that indicate the presence of water vapor in the atmosphere of this exoplanet.
Incredible. But it's one thing to identify single elements or simple molecules, but deciphering whole foreign bodies like Dr. Owajawik.
How do you know? Oh my God, it took us a very long time to figure this out. It really took us many, many decades, and it took us many, many fantastic new instruments.
If all of our astrophysical objects, or anything that we're looking at, were made up of one element, this would just be so easy. But we don't. So we have to do experiments on Earth like this to prove what we're looking at looks like what we are thinking we're looking at. So in here is argon. If we turn it on here, it glows this really pretty purple. And then if we look at it with a spectroscope, it shows us a very specific fingerprint to argon. These are called spectral tubes. My bounty of tubes. They contain the gas of one element, and the box runs a voltage through the tube. When I turn on the switch, the charged gas turns to plasma and emits a color that is unique to that one element. It also makes unique lines when you look through the spectroscope. And this one is helium. This same process happens in a star or a hot region of gas. So we use tubes like this to verify what we see in space. If you do a quick search for spectroscopy data, there are numerous ways that the data can appear. Those variations are based on the source of the cosmic light. There are 3 types of spectra that we can use: continuous, emission, and absorption. Light from a hot, dense source, like the sun, produces a continuous spectrum. When that light passes through cooler gases on its way to us, the gases take away or absorb some of that energy. Dark lines appear where specific colors are missing. And when thin gases glow themselves, we see only their characteristic colors, kind of like a cosmic barcode. These are the emission spectra from pure elements that were given a voltage to glow, just like my spectrotube, but way better. Like all data, there is an art to analyzing spectra. Scientists like Dr. Owajawak use computers to calculate and tease out clear signals, comparing them then to models that are already known.
There you go.
Many scientists in the labs on Earth, they try to recreate the same conditions and measure basically what these kind of, as you said, fingerprints of those different transitions for different elements are.
Okay, so we're always comparing to sort of the fingerprint of what we have, and
Yes.
then if it has deviated from that, that is the new information from what we're looking at.
Correct.
For Anna, spectra unveil the structures of black holes, the swirling winds that surround them, and those big jets of particles that come out of them. When you look at a black hole,
Yes.
this is what you see.
Yes.
Where's the accretion disk? Where are the
Yeah.
winds?
So all of this is mostly accretion disk at this level. It's just different parts of it. We can zoom in, right? And we see all of the absorption lines, right? All of these lines are also shifted a lot. So they come from this wind that we saw in the first picture. So that's how we know that there is winds blowing around black holes.
The same principles apply no matter the wavelength of light. But each wavelength of light tells us a little something different about each character we find in the universe. It's pretty wild how different the universe looks to our eyes and how it presents to our telescopes. And that's precisely why we need to observe in different wavelengths of light. Modern astronomy is built upon spectroscopy. So with every stream of light we gather, we further understand what the universe is made of. All we need to do is pry open its contents.